Swayam Prabha. Digital India. Educated India.
In the previous module, we have seen how to balance the inertia forces in a mechanical system with an objective to make the operation of the system smooth without any vibrating tendency. That not only improves the functioning of the system, but it also improves the life. However, the job is not complete. There are other sources or there are other reasons for non-smooth operation of a mechanical system, and in this module we will take up that particular problem and also try to see how the problem can be either minimized or removed. If we take a mechanical system, then its condition can be generally specified by two things, that how much power input is there and how much power output plus losses. So what is happening in a mechanical system, irrespective of the nature of the system, there is power input from one side, that means which is putting energy into this system, and the mechanical system is doing some work and spending energy, and in between there will be some losses because of friction, etc., within the system. Now, what are the different situations possible? If we consider that with time power input is something like this, and the requirement of the energy for doing the task and the losses are something like this. Now we know that if we are putting energy at a higher rate than the rate at which energy is being consumed, what is going to happen? We all know that energy can never be destroyed, so it is going to remain in the system. It will get accumulated in the system, and obviously a mechanical system can accumulate energy in the form of kinetic energy. So what is going to happen? The speed at which this mechanical system is operating will gradually change, and in this case we will find that with time the speed of the machine will gradually increase, because with time more and more energy is going to remain into the system and resulting in gradual increase in the kinetic energy, that is the speed of the system. The reverse situation is there where it can be less. Just repeat the same diagram, only in this case now your power input is less and power requirement or the expenditure of the energy is at a higher rate. And this is the power input. So, the reverse thing will happen here. That means, whatever energy or the rate at which we are putting energy into the system, we are consuming energy at a higher rate, and where from that extra energy is going to come? Obviously, whatever kinetic energy is there in the mechanical system, part of that will supply the deficiency. And as a result, we can easily understand that in this case with time, the speed of operation of the machine will slowly decrease. Pretty obvious. Both these types of operations are called unsteady operations. You can see that when we are starting an engine, initially the speed of the engine was say 0, then gradually it increases. So, during that period we have to put more energy into the system to bring the level of operating speed of the system to the final steady level. Similarly, when we stop some mechanical system, so what will happen? Your power output will be there because work is still being done, but power input has been switched off, and so therefore slowly the speed will come down. These are the transient periods at the beginning and the end of operation. But during the actual operation of a machine, what happens? We expect the speed, operating speed of the machine overall must remain same. So, in real situation, though we have shown the diagrams like this, in real situation the speed is never that steady. So, this is the rising curve and this is the falling, something like this. But what we are concerned primarily is when the speed of operation of the machine remains constant, that is steady operation. The ideal steady operation will be like this. With time, the energy input is like this, and energy output and losses also equal. So, this is the idealized situation for steady operation. And the speed of this case will be just again constant. But we all can understand that in reality such a perfect situation is never realized. What happens is the average of the power input and average of the power output plus losses will be same, and the speed will be also, therefore average will remain same, though there will be fluctuations. What is that situation? Let us examine slightly in more detail. Let us take up a case where the situation is like this. With time, the input and output power variations are something like this. This is a one complete cycle, and so this is the output power, and this is the input power. What we can realize that the average will be same for both the input and output. So this is both the average of input and output power. Fine. Now what is going to happen to the operation of the system? That means the speed of operation. Now we see that there are, though the average for both the input and the output powers are same, there are locations where, that means at every instant except for this instant, and this instant, everywhere else the instantaneous input power and instantaneous value of the output power, they are different. So what will happen is that depending on the situation, the system will either accelerate or decelerate, except at two instants where the input and output powers are exactly same. So what is going to happen during this period where output power is more than the input power is obvious, the engine speed will come down or slow down. Similarly, in this period, that means from here to here, this is one cycle, because in steady state everything will be in cyclic pattern. This is one cycle, after which the pattern repeats. So here what will happen, input power is more, so obviously the speed will increase or the system will accelerate. So therefore, what the situation will happen will be like this. So speed is constantly decreasing from here to here because output is more, and speed is increasing here because input is more. Therefore, you can see that in general, where the output power and input power instantaneous values do not match at every instant, but the averages are same. So though the average speed will remain constant, but the instantaneous value of the running speed of the system will change or fluctuate, and there is a cycle after which the whole thing will repeat. This is in general is the situation with all cases. So therefore, we find that we have now a non-steady or rather non-smooth operation. The operating speed of the system is fluctuating. In previous case where we discussed the balancing of unbalanced masses, the nature of non-smoothness was due to the shaking forces produced by the unbalance. But here the non-smoothness of the operation is because of the operational speed is fluctuating, and this is the reason for that. So now I think let us consider the cases which we will generally encounter. In general, we will find two types of cases. Of course, this is the most general situation where both the output power and input power, they are both varying like this. But in general, we will take up the cases often encountered. There are two situations. one in which the input is fluctuating and output power is uniform, one cycle, and the other situation, idealistic situation of general nature, is the input is constant and the output or input is constant and output is fluctuating. In both the cases, of course, we have to keep in mind here, because it is a steady operation, this is not only the input power, but this is also equal to average output. Similarly here, this is the not only the output power, but it is also equal to the average of input power. So these are the two generally encountered situations in mechanical dynamics or machine dynamics, where in one case the input power is fluctuating, output power or the load is constant, whose average value happens to be equal to the average of the input power, because otherwise the situation will not be steady. The speed will slowly change, not only just fluctuate. And the other possibility is that where the input power is more or less constant, but the output power or the requirement, the load, is fluctuating, and again the same condition for steady operation, that the average of the both are same. Now these two possible cases we can think of examples. Now we can get very common examples in this case, say where the input power is fluctuating, the output power is uniform or steady. Very common example of that will be an engine, an IC engine driving a generator set. Producing electric current, and the load is constant, and this is the IC engine, say diesel engine. Here you will find the mechanical torque produced on the crankshaft is fluctuating, that is input power is fluctuating, but the load or the resisting load produced by the generator is constant, as our electric load is constant. So this will represent a situation like this. Here on the other hand, if you take up a case where a motor is driving a punching machine, for example, a die punch machine. So here what happens, motor is producing a constant voltage and constant torque, so input is constant, but the load requirement is fluctuating. Most of the time there is no load except friction, then once the punch comes in contact with the plate or the sheet metal, immediately the load starts increasing. So here you will find that the situation is something like this, and in such cases situation will be like this. In both the situations the speed will fluctuate. Our objective of this discussion is to find out the ways and means to estimate the speed fluctuation and how we can keep it within tolerable limit. The point we have to keep in mind is this, that though the average speed remains constant, the instantaneous speed varies and it fluctuates. Now, depending on the operation, there are permissible limits to which we can allow this operating speed to fluctuate. If the operating speed fluctuates too much, then the functioning or the performance may not be acceptable. And therefore, we will see what can be done to keep that fluctuation of speed within the permissible limit. So, we will first take up the most commonly encountered situation, that is an engine driving a mechanical system, either a pump or a generator set or a machine or something. So, we will take up the very commonly encountered problem of the nature we are discussing, is the power smoothing of single cylinder engines. So, what we will do first is to find out the fluctuation of input power in case of such a situation. So, we will again come back to our model of So, this represents a single cylinder engine. Now, what we have done, if you remember our previous lecture while discussing the unbalance of a single cylinder mechanical slider crank mechanism, we saw that it is possible to replace the mass of the connecting rod AB into two parts, one at the crank pin here, other at the reciprocating mass here. And we have seen that this mass, the crank's original mass, all these are actually purely rotating objects, and therefore, to balance that we always generally put a balancing mass, but really it does not play any role in this analysis which we will be doing. On the other hand, the other apportion mass which goes here, that along with the mass of the piston etc., in total becomes reciprocating mass, that we have seen. Now, what we will do here is to find out that if a gas force, which is the pressure at the instant of the gas within the cylinder, multiplied by the piston area A, this total gas force produces how much turning moment on this. The reason is this, that turning moment M that multiplied by the speed gives the power input. Now, if we are considering a case where we consider the input speed or the running speed omega to be constant, approximately constant, then what really tells about the fluctuation of input power is also the fluctuation of turning moment, which is that because input power is nothing but m into omega. So, when we take this as constant, then fluctuation of m or turning moment is the critical thing, and that is what we have to find out. So, to do that, we again take care of certain point like the lambda is r by L, which is much smaller than 1, and omega is constant approximately. It cannot be exactly constant, approximately constant. Now, let us draw the free body diagram of the various bodies. This is the piston, this is the connecting rod, this is the crank. Now, what forces are acting here? Is E into A. Now, since we have replaced the connecting rod by a massless rigid rod, and the mass of the connecting rod or this coupler AB being placed at here and here, so effectively this is a massless rigid connecting rod. So, therefore, any force on this has to be along this. We know that. If we call this force Q, then equal and opposite forces will act at B. The force on the piston and the reciprocating mass will be in this direction, and the normal reaction from the cylinder wall, these three forces will be producing a resultant force in this direction, because it can accelerate only along this direction, which is x. So, therefore, total force along the y direction has to be 0 according to Newton's law. Now, the Q, which is aligned along the connecting rod, has to be again balanced by equal and opposite force at the other end, because this body being massless, it cannot accept any resultant force acting on it. And according to Newton's second law or third law, the force at point A will act, which is again equal and opposite to this. And this we consider this as, so the turning moment is going to be this force Q into the perpendicular distance of this line of action of this force from the hinge crank point, and that is the turning moment. So, therefore, as our objective is to find out the turning moment M acting on the crank pin, so let us find out first Q. Now, the resultant force on this will be in this direction, which is F. It has to be in this direction because the piston can accelerate only along x direction. So, we know F is equal to Q. Now, this angle is phi. So, Q cosine phi minus PA, and that must be equal to the reciprocating mass into the acceleration in that direction x2. Now, in our previous module, we had a detailed discussion on the acceleration of this sliding body x2 dot, and we found out that x2 dot will be This result I am not going to discuss again because we have derived it in the previous module. So, using this, we can write now that Q will be approximately equal to PA minus M reciprocating So, we have found out the force Q. Now, what will be the moment produced by this force about you? What is this moment produced? That will be Q into how much is this distance? Now, if you take up this right angle triangle, this angle is theta. How much is this angle? Phi. So, this total and this angle is theta. So, this perpendicular distance OC is nothing but R sine theta plus phi from trigonometry. This perpendicular distance, this angle is theta plus phi, so it is nothing but R sine theta plus phi. And we can write this is equal to, therefore now, this is the expression for the turning moment, which you can see is actually a function of theta. That means it varies with theta. But I think here we have another quantity which also is varying with the time, is that phi. So, let us try to see if it is possible to express turning moment purely in terms of theta. The turning moment diagram expression we have got is seen as a function of theta and phi, because this gas pressure here acting on the cylinder is also a function of theta, as you will see. However, it may be desirable to express the turning moment completely in terms of one variable only, theta, because theta and phi are dependent. We can do it in this particular way. Say the moment of this force Q about this point O is obviously the magnitude of Q into the perpendicular distance from this point, this crank pin is OC. Then you will see that we can find out this point D, which is nothing but the intersection of the extension of line DA with the perpendicular drawn on the line of stroke, that is the x-axis. This is the point D. We can easily show that this point D is nothing but the instantaneous center or relative instantaneous center between link 2 and link 4, that is the slider or the piston. Say here we know that turning moment is approximately the force Q, which is PA minus M reciprocating omega square R cosine theta plus lambda cosine 2 theta divided by cosine phi, this is the force Q, into the perpendicular distance OC. Actually, in this r sine theta plus phi is nothing but OC. Now, from this triangle, right angle triangle, we find that this angle is a right angle triangle OCD. This is the right angle, this is angle phi. So, this angle will have to be 90 degree minus phi. And since this is 90 degree, this angle is nothing but. So, we can write now that OC is OD cosine phi, or OD is equal to OC by phi. So, therefore, using this, we can now write this is equal to now OC by cosine phi is nothing but. So, we have to now find out OD as a function of theta, then our objective will be fulfilled. Now, you are familiar with the technique of using Aronhold-Kennedy's free instantaneous center theorem for finding out those relative instantaneous centers which are not known. Now, in this slider crank mechanism, this is the fixed link 1, this crank is link 2, connecting rod or coupler is the link 3, and the piston or this slider is link 4. So, directly we get the relative instantaneous center between link 1, that is the frame, and link 2 as this hinge. Between 2 and 3 is this hinge, between 3 and 4 this hinge, and the relative instantaneous center between the fixed frame 1 and 4 will be at infinity in a direction perpendicular to the axis x as indicated here. Now, we know from Kennedy's theorem that to find out an instantaneous center between two objects can be done by using this theorem that the three relative instantaneous center between three bodies must lie in one straight line. So, if we want to find out the relative instantaneous center between link 2 and link 4, that means 2, 4 if we have to find out, how can we find out? Now, considering link 2, 3 and 4, we know that 2, 3, 3, 4 and 2, 4 must lie on the line joining 2, 3 and 3, 4. So, this is the line 2, 4 on this. Again, if we consider links 1, 2 and 4, then the instantaneous center 1, 2, relative instantaneous center 1, 4, if we add the other relative instantaneous center between these three bodies 2, 4 must lie on this particular line. Now, if we join 1, 2 with 2, 4, 1, 4, which is at infinity in this direction, we will get nothing but this line. So, 2, 4 on this. And therefore, the solution is. Now, what does it mean? It means that a point attached to link 2 but located here has the same velocity as a point attached to link 4 located here has the same velocity. That means, what is the velocity of a point on link 2? Now, link 2 is having an angular velocity omega. So, the velocity of this point will be omega into OD. and velocity of this slider, because it is a translating body, is also same as this, and we know that this is nothing but x dot. So the velocity of this point has to be the velocity of this slider, because it is a translating body, and velocity of all points of this translating body 4 is x dot. So we find, but unfortunately we have taken x in this direction, so positive x dot will be in this direction, whereas with the given omega, the value of omega into OD is in this direction. So we can write that omega into OD equal to minus x dot, or OD is nothing but minus x dot by omega. So using this here again, we can therefore write this is equal to PA minus m reciprocating omega square r cosine theta plus lambda cosine 2 theta, and OD will be equal to minus x dot by omega. Now let us recall our memory from previous modules, where we derived the expression for x dot in terms of theta and omega and r, and we know that x dot was minus omega r sine theta plus lambda by 2 sine 2 theta. So finally we get turning moment is approximately equal to PA. P is a function of theta, that is the gas pressure, A is the cross-sectional area of the cylinder of the engine, reciprocating mass omega square r, and minus x dot by omega is nothing but r, so thus we find turning moment as a function of only one variable, that is the crank rotation angle theta, the crank rotation. How it looks like, let us see. To do that, first we will consider the most commonly used engine, that is a single cylinder 4-stroke cycle engine, which is operating on the Otto cycle, that is a petrol engine. Let us see. And as mentioned, let us take up the case for a 4-stroke cycle petrol engine. So, because why we need this is, here most of the things are just purely of geometric nature, except this gas pressure. This is the gauge pressure, that is the pressure above atmospheric in the cylinder, which is actually also a fluctuating thing, which changes with theta. How it changes, that we can see if we look into the Otto cycle. Now here, suppose we know that now the piston displacement is in this direction, and since the cross-sectional area of the cylinder is constant, this in a way also represents the volume of the gas inside. So actually the pressure here and the volume, the PV diagram of a petrol cycle or Otto cycle, how it looks like. Only thing here on this side will give piston displacement, and on this side we will have P plus if this is the atmospheric pressure, then you know first stroke is a suction stroke, where the pressure inside will be slightly lower than the atmospheric pressure, partial vacuum is created. Then there is compression stroke. Pressure increases because the valves have been closed. Then there is firing, and this is the combustion stroke. This is the firing. And next is the expansion, where pressure comes down, and the last stroke is exhaust, where again the piston pushes out the burnt out gas, and again to push it out into the atmosphere the pressure has to be slightly above atmosphere. So if this be the typical Otto cycle on which the petrol engine runs, what will be the nature of the turning moment? So since it is 4-stroke cycle, total range of or value of theta for a complete cycle will be 4 pi. So P or PA, whatever it may be, let us plot PA. So we can see it will be nothing but this multiplied by the area. So the nature will be more or less same. So if we spread it out, it will look something like that, E into A. Now, what we have now we have to subtract this. That is the inertia force. This is nothing but the inertia force. And that is going to be something like, depending on the speed, now when you add these two, so it should take a shape like this. this will be PA minus m reciprocating omega square r just the summation of the two others. Now we have to multiply this by r into this quantity. How this quantity changes? That quantity changes in this form. So, finally the turning moment will be nothing but the product of this and this value. Thus, we can draw the final turning moment diagram. Now, we can see this is 0. So, obviously, this is a point which we will have. Then again this is 0, obviously it has to pass from this, and this is negative, this is positive. So, it will be something like this. Then this is again 0, so it has to pass through this, and here this is negative, this is positive. So, the whole thing up to this will be negative. Now, both are positive, so it will be now positive, but it will again become 0. So, therefore, it will be something like this. And here again one is negative, one is positive up to this. So, it will be 0, and here both are negative. So, therefore, the product. So, this is the final turning moment. Thus, we can see that the turning moment fluctuates, and the average value of the turning moment will be something like this. Or if you think it is slightly on the higher side, perhaps it will be somewhere here. That means total area bounded by the black curve and the red line above and below will be same. Now, it is quite clear that in such a situation there is substantial amount of fluctuation of energy. Here the load is more than the input up to this, then it is slightly input is more up to this, then again load is more than the input, then here input is more than the load, and so on. And therefore, there will be substantial amount of fluctuation of speed with such. Now, in the next lecture, we will see that how we can find out the resulting fluctuation in the speed of operation of the engine, and also we should be able to find out that what is to be done to keep the speed fluctuation resulting from such a situation within the permissible limit.